Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to today's episode. Today I'm joined by Helena Milevych and Jakub Nalepa from satsearch member KP Labs. KP Labs is a Polish new space business founded in 2016, and it develops autonomous spacecraft and robotic technologies. Today we're going to be discussing how to create a hardware and software ecosystem in order to bring AI-powered algorithms for autonomy into space missions. Really, timely topic, a topic that a lot of businesses are grappling with and thinking about for the future. So, Helena and Jakub, welcome to the podcast. Is there anything you'd like to add to that introduction?
No, hello. Thank you very much for this introduction. I think you perfectly describe what we are doing as a company.
Okay, let's get into today's topic. So, from your perspective, how mature do you think AI systems are today that can be implemented in space missions? Could you maybe, break down what AI-powered algorithms for autonomy, what this phrase really means for missions today against existing capabilities, against the operations that we're more accustomed to?
Yeah, I think that's a very great question. So probably we can break this AI algorithms into different specific parts because it very much depends on the mission that we are trying to target. So we have quite a bunch of different missions. Like, for instance, for Earth observation, we may employ AI at different levels. For instance, we can think of capturing a very huge amount of data on board the satellite. So given the huge amount of data, it's nice because we can try to extract some useful information from raw data. It is also difficult to transfer and to analyze on board and to take some actions based on this data that's captured just in orbit. So this AI for, let's say, non-critical missions like Earth observation might be used for extracting knowledge from raw data on board the satellite. And basically we can quantify the maturity of AI using, for instance, TRL, which is technological readiness level. And also we can break down AI into different parts, as I mentioned, and different algorithms are at different maturity levels. For instance, if we analyze image data, we are pretty much advanced because we've been doing this for years for different image modalities. And now we are in the process of deploying such algorithms on board, which is not obvious because we are in a very extreme execution environment. So we need to make sure that the algorithms are robust enough to be deployed in space missions, which is very different from the Earth, like on the ground applications. So we are actually getting there, but there's still some things to do depending on the mission and on the characteristics of a specific mission that we are just about to target.
And I would also like to add some examples. While we're speaking about missions, there are also some other examples how we can use AI in space. And I would like to bring here a few examples that are not only mission related. For example, in 2018, for example, German Aerospace Center, DLR, launched Simon to the ISS, to the International Space Station, which was a crew interactive mobile companion. And it was able to see, to speak, to hear, to understand, and of course to fly. It stayed for 14 months. And then it was followed up by the Simon 2. So I think it's another example how we can use AI in terms of assisting people and, to support astronauts. And there is another example also related to the ISS, but this time by JAXA, by the Japanese Space Agency. And it is called Int Ball. As you can imagine, it is a ball. And it also supporting the astronauts on the International Space Stations with taking pictures or taking videos. So I think we're already experiencing this AI in space, but not only in missions, but there is a wide range of different scenarios how we can use it. For example, NASA also cooperated with Google to train AI algorithms to search for new data from the Kepler mission. Or, for example, we have the project that is called Artificial Intelligence Data Analysis, that aims to search data from ESA, from the European Space Agency, and from NASA, from all around the solar system to bring new discoveries, to reveal different anomalies. So I think it's already happening. Maybe it's not a mass scale, but it's already there. And maybe I will also bring a few examples from our company, from our activities, what we are doing. So here is an Antelope. This is an onboard computer with the DPU module that aims to analyze the telemetry data. And we submitted our idea via the website Ideas by ESA. So we want to hold such experiment to analyze the telemetry data from OPSAT to search and to train to understand whether we can predict the anomaly in telemetry data. As you can imagine, the more satellites we have, the more difficult it is to get these anomalies for an operator. So this is one example. There's also a few other examples like super resolution reconstruction for a single or multiple images. There's also hyperspectral image segmentation. And I think there are more and more examples, but maybe the real scale we'll see in the upcoming missions.
Also, I can add something on that because Helena brought an interesting example of Antelope, which is this system for detecting anomalies from telemetry data. Because it's not only about training and deploying the models on board the satellite, but also how can we trust that kind of algorithm operating on board the satellite? Because we definitely don't want to lose a satellite. We need to prove that it can actually work in the wild. And for this reason, the verification and validation process is like super important in the deployment chain, because we need to prove that things will ultimately work in practice. That is a critical component in space missions.
Yeah, absolutely. We talk about this all the time from the hardware perspective, but as you say, it's equally as important from the software or even the algorithm level. And a very interesting concept that you mentioned there, discussing the TRL of the individual algorithms. I think we break things down to that level of granularity, but if the algorithm is so critical to the success of the mission, then of course it's vitally important. And thank you for sharing all those examples as well. I think quite often we discuss uses of onboard AI and onboard processing for Earth observation, but yeah, there's many more examples out there, many more different types out there. So maybe we've discussed individual missions there. Perhaps if you wouldn't mind touching on some of the types of missions and in particular the technical requirements that you see in the industry that would require, autonomy or would benefit from autonomy-based AI on board.
Yeah, I think it's a very interesting question. And probably at this point, we are mostly thinking about the Earth observation missions. But what we also see in the industry is that more and more companies are looking for different types of AI-based missions, like in-orbit servicing, like space debris removal, like asteroid mining. Maybe this is a very future concept, but we already see missions that are working towards this direction, or for example, deep space missions. For example, if a satellite somewhere, when we cannot reach it easily, then some level of autonomy and some level of AI is really useful. For example, we have more and more lunar missions. We're speaking about Martian missions, and this is the point where it is really useful and it's really helpful. But in terms of requirements, this is a very interesting point, I would say. And we're looking for a trade-off between the power availability on one hand and computational power on the other hand. For example, in terms of in-orbit operations, like manufacturing, like, printing in orbit already. We have to think about this balance, what we expect and what we can have in terms of hardware and software. And I would also say that at the moment, our company is looking for CubeSat format, but of course, we are also thinking about bigger satellites. If it goes for the requirements while talking with different partners or clients, we see this sensor-specific approach because there are different types of sensors. Of course, there is multispectral, hyperspectral, RGB, LIDAR, radar. So there are all the different types of payloads that you have. So we also have to think about this, to take it into account. And this is another issue, right? Because we have a lot of different interfaces that we have to create, to develop. So I would say that at this point, it's very much about trade-off between what we can get at this point and what the industry wants from us. But of course, the huge advantage that we see is the reprogrammability thanks to the FPGA, because the thing is that our computers, our hardware is based on the FPGA. So when the satellite is already in orbit, we can reprogram it. It means that the same satellite could perform different, let's say, actions, different mission goals within the same mission. So, for example, half of the orbit, the satellite is doing, Earth observation, and then, for example, shipment tracking. So there are different things that we can work thanks to the AI, thanks to this, let's say, agile approach. And what else I can say here is that in terms of mission types, we are first of all thinking about the missions that are looking for fast response, for maybe near real-time data. And this is where this onboard data processing is really useful and helpful.
Yes, also it's important to understand the benefits of employing AI on board, because we are bringing that kind of data-driven algorithm on board, and what can we actually get out from this. Helena brought an important point of real-time processing, because in specific applications, it might be the case that for example, the data that is old, it is not useful at all. So we need to get this data as fast as possible to actually extract some value from this raw data. And that is where AI could help. It could accelerate the process of downloading important information from the in-orbit operation.
Right. Great. So this is the reason why, as you say, time and effort is invested in ensuring it works on board as opposed to on the ground, which is, this is really interesting, really. And highlighted again, as we hear so many times, space is about trade-offs, isn't it? And that's important to remember at every stage of mission design and development. Now, at KP Labs, you've developed something that is described as the Smart Mission Ecosystem. I wondered if you could describe this just briefly for us and explain what the parts of the ecosystem are and how it ultimately delivers value to space missions, accounting for these trade-offs that we've mentioned, maybe some of these use cases that you've discussed earlier.
Yeah, so maybe let's start from the explanation. What's the Smart Mission Ecosystem? So it consists of 5 elements: software part and hardware part. So let's start from the, let's say, very top. This is Oryx, which is onboard computer software. And then we have Antelope, which is onboard computer with the DPU module that already was mentioned today. And there is also Leopard, which is a data processing unit. There is also Oasis, which is EGAC. Unfortunately, will never fly and will never see the space by its own, by its supporting the mission integration and checking the whole system. Then everything works fine. And of course, there is the Herd. It's a bunch of different AI algorithms for the Earth observation, but not only. For example, as we already mentioned, algorithm for the telemetry data for this analysis. And maybe let's speak about the motivation behind it. So the thing is that while building our own mission, Intuition One, we mentioned that there is a new space and there is a CubeSat format, but the thing is that the flight delivery chain is very fragmented. And even if you buy different components, different subsystems from different companies, at the end, you still have to do some work from your side. You have to adapt the software for your mission. You have to get these additional efforts so everything works correctly. So we came up with the idea that it might be a good idea to create an ecosystem where everything works with everything. And that's why we call it ecosystem. And we think that the crucial here is that thanks to these components, we can bring missions faster and cheaper, which is quite important in terms of constellations or even mini constellations. And then again, you spend less time And the missions are safety, because there is no need to create everything from the beginning. You just it's like a puzzle. You just bring different components, and they are already developed the way that they interact with each other and they speak to each other.
Yes, the idea is to just keep the brain very close to the eye, because we are capturing the image data, which is huge. It might be difficult to downlink, as Helena just mentioned, and the idea is to process as much as we can on board the satellite to extract value. And this value might be very different and might be dependent on the use case, and actually will be dependent on the use case. We'll extract different value for agriculture, for object tracking, etc. So also the idea is to uplink the pre-trained models just back to the operating satellite, so we can perform training on the ground and then uplink the model straight to the satellite, because we'll be ready for using deep learning on board. And then we can use pre-trained models on board to actually process the new data that's coming from the sensor, which will also mean that we can decrease the amount of data transfer. As I mentioned, it is important because we want to get this data as fast as possible in the real time, if possible. If this is happening, we can take faster actions in specific applications, which might be crucial, because otherwise the data would not be useful at all if it's, for instance, delivered too late back to the ground. So that is why we are bringing the operations on board satellite, and we want to not transfer the entire data, just the important bits extracted from this data on board Intuition One.
That's great, and that's a critical challenge that, as you say, satellite integrators face when using components from different suppliers. So thank you for describing the ecosystem there. And I love the names of the individual names of the products as well. The leopard, the oryx, the antelope, and then the herd, where it's all come together. Alongside the development of this hardware and software ecosystem, I know KP Labs is also developing its own mission, Intuition One, in order to demonstrate some of this technology. Could you just describe to us some of the key features of this mission and what you're looking to achieve with it?
So maybe I will start from the introduction of our mission. It's a hyperspectral mission with the onboard data processing. And the idea behind it was that while we have 150 bands, it is quite difficult to downlink all the data to the ground station. So we came up with the onboard data processing chain that later on became the herd and leopard itself. And the thing is that it is a 6U CubeSat, and it is about to launch in the very end of 2022 or at the very beginning of 2023. And the idea that it might be considered as a flying lab, because thanks to this reprogrammability, we're able to check different scenarios, like agricultural scenario or any other scenario where the hyperspectral data is required, thanks to the leopard that could be easily reprogrammed, and thanks to the algorithm that could be pre-trained and uplinked to the satellite. And I think it also important from the other perspective, because some of our products will get the fly heritage thanks to this mission. Of course, in terms of oryx, it was already tested in orbit in the end of 2020. But for example, the herd, it will be fully deployed on the Intuition One. Of course, we have smaller projects with ESA at the moment to be prepared for this. But anyway, for the first time, the antelope will fly in full, let's say, size on our own mission. So I think it is very important for us, and it is challenging project in itself. But I think it's also quite fascinating, and we're gaining a huge experience while developing it.
I could actually add that I liked the flying lab Helena mentioned, because it is exactly what we are trying to do. We are trying to build the satellite that is application agnostic, so we can uplink any algorithm given that we have the data to train on, and we can deploy any type of deep learning algorithm on board the satellite, which would be, I think, exciting, because we could target different applications that are most related to Earth observation, but we can actually do anything with the hyperspectral data that we'll be capturing on board.
Brilliant. Well, best of luck with the mission. It's an opportunity to demonstrate a system that could potentially have more value during the mission timeframe due to the ability to upload the new models, the new algorithms, or retrain the algorithms and uplink them. So the value in year 2 of the mission could be higher than year 1, which is great because normally a satellite's launched and it's launched. So that's great. Well, and on that, I think the sort of value that you're talking about, where do you see that being utilized in the industry? What are the typical profiles of customers that you're looking to service with the smart mission ecosystem? I know you've given us some examples already of the types of missions, but yeah, maybe if that can use AI on board and onboard processing, etc. But maybe just to focus a little bit on the smart mission ecosystem itself.
First of all, we are looking for a new space market. And right now we are focusing on CubeSats. Of course, in the future, we want to expand the product line and we want also to cooperate with bigger satellites. And this is the idea. But at the moment, we are focusing on CubeSats, and it might be, cooperation from different levels, from different angles. We are very open to the cooperation with the commercial missions, but from our point of view in Europe, maybe it's not at the level that we would like to have. So I would say in Europe, we are mostly focusing on students' missions and on agency projects. This is the European reality. But we are also looking for different mission types. And as we mentioned here, it might be some feature extraction for the Earth observation. It might be missions where near real-time data is required, for example, in terms of crisis management or flood monitoring, or as Jakub already mentioned, it might be agricultural use case scenario when we are speaking about soil mapping. So there are a wide variety of different mission types. So I also think that it's a huge advantage of this ecosystem that it might fit to different mission types. And of course, the idea that in terms of Earth observation, well, I found such data that right now only 5 to 15% information or data that is sent to the ground station is useful. So it means that we have a lot of satellites, but the data that is sent to the Earth, it's not that much. So the idea that we want to have a better quality, for example, thanks to the cloud detection algorithms, instead of sending all the data to the ground station, we can send only data and pictures that is useful, right? So instead of having all the pictures in this chain, we can focus on pre-processed pictures that would be really useful. So I would say that cloud detection or bad pixel mitigation, it's a great example on how we can use this technology right now, not in the future, not in 10 years, but right here, right now, it is already available. And I think it will bring additional value to almost every mission.
As you say, that it's about increasing the value of existing missions and existing technologies simply by increasing the value of the data. So that's fantastic. You spoke there about the customers you're looking for today and the shape of the industry and the market today. Just to finish up, if I could put you on the spot a little bit and ask where you see the market for AI-powered autonomy in space missions, the sorts of use cases examples we've discussed today. Where do you see it going in the next 3 to 5 years?
I think in terms of space, 3 to 5 years is quite a short perspective. Yeah, and I would say that most of the missions that we'll see in this time frame, they're already planned and they're under development. And if we look at the different agencies' strategy, then we can see what's about to happen. And there is different an interest in AI missions. And there is also another statistics that I found that over 10,000 satellites will be launched within the next 10 years, where around 1,000 will require the onboard data processing. So we can see that there is a huge potential for such applications. And in terms of our own missions and our own, let's say, products, I can highlight FISA-2 mission. This is an Earth observation mission where our algorithms, the Earth, will fly on. There is also an offset mission that I already mentioned today before. And we submitted this anomaly detection scenario with the ideas by ESA. There is also a hypothetical, let's say, scenario where we can use our Leopard. This is space debris removal. We see more and more missions, also European, but not only, that are interested in cleaning, let's say, the space and making space more safety. And I would say this is crucial because if we have unoperated satellites, more and more unoperated satellites, it is quite difficult to maneuver. It is quite difficult to use the space. And so this is another example. And what's more we can add here is PWSat-3. This is a mission in cooperation with the Polytechnical University of Warsaw, and our Oryx onboard computer software and an Antelope computer with the algorithms are about to fly there too.
Fantastic. Well, I think that's a great place to wrap up. And thank you both for sharing all these insights with us today. It's been really interesting to learn about how KP Labs is developing the ecosystem and looking to bring onboard data processing into more application areas. And obviously, best of luck with the Intuition 1 mission for your own demonstration purposes. And just wanted to thank you both for being with us on the Space Industry Podcast today. To all our listeners out there, you can find out more about KP Lab on the satsearch platform at satsearch.com. Feel free to use the request function on the platform for any questions you might have and any expressions of interest in the company's technology or for documentation and whatever else might help your procurement journey. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.